Hey guys, this is Coach Carroll here with a short tutorial video over the SAGE part of your engineer mechanics project. Now hopefully this document looks familiar to you. You should have read through this document already, hopefully before you ever even started the project. Read these sections about why the project is important, and especially this section here about the requirements. The requirements section goes through and talks about what I want to see in the report. You'll have to write a nice neat report on this that is typed up on the computer, and here's all the sections of the report that I want. So it's outlined for you, everything that I want about how long I'm looking for it. So make sure you read through this. I'm not just going to read it here in the YouTube video, but make sure you look at this so you're aware of what you're needing to calculate in the first place and what I'm looking for the final report. Now the purpose of this video is that if you've looked at this document, which is on Moodle, this document is the SAGE calculations for the error quantification that for that example experiment that I did in class right before the midterm. So if you have your notes from class for that example problem, this is the SAGE document that I would be looking for your project if that was your project. Now, if you've started to look at this document and you say, I have no idea what to do, this looks too big, I didn't even learn SAGE back in engineering skills in the first place, someone else did it for me, you need to actually learn it now. Well, if this is too intimidating for you, this video is going to start from scratch and use the skill that we hopefully learned in engineering skills, that if a problem looks too complex, start out simple and just build on each step that you understand. So we're going to start from scratch, and instead of using this example that I did in class, since you already have this full document here, I'm going to do another example. But just one more note before I move on. These comments here in this PDF will be very helpful to you. They explain what every line of code does. They give a lot of explanation into things about SAGE. So if you aren't one for watching videos, if you're reading this document, reading these comments, it should walk you through very well about how to do the SAGE for your project. It's not too complicated, so let's not get too confused about it. Here's the experiment that I'm going to use in this video just as an example. So let's say in this experiment we have one beam and it's supported here on this end at B, and then there's a scale that's supporting it at point C, and there's nothing else touching the beam, so the only thing that's creating a force is the weight of the beam. And so this scale will measure the normal force here at C required to support the beam in equilibrium. Now there's some measurements about the beam that I would have taken. One of them is the mass of the beam, so it's 4 kilograms, and the uncertainty of that measurement is 0.1 kilograms. Now here's some other distances I'll need that I've measured. This 2.6 meters is the length of the beam, 0.7 and 0.4 on either end here. Now the uncertainty for each of those measurements I've written down is 0.005 meters. Now of course your uncertainties may be different based on what measuring tool you use, based on how accurate you're able to use those measuring tools. And you may have a different uncertainty for the length of the beam or for the measurement from A to B and C to D. But just for simplicity in this example, I'm going to use this uncertainty for all three of these links here. Now let's say I set this experiment up and I read the scale, and the scale reads 15.4 newtons. Now let's say because of the tick marks in that scale, that scale is only accurate to some precision. So the smallest tick mark divided by 2 for this case was 0.2 newtons. So I read 15.4 newtons with an uncertainty plus or minus of 0.2 newtons. Now I want to actually predict this using theory. So this is the experiment. Picture I've done this experiment, set the beam up, taken my necessary measurements, read the scale, and here's what I get. Now I want to predict this. So first, before you ever even get to SAGE, let's just do it by hand. Well, to do this, I need a free body diagram to model it. Okay, so I draw a free body diagram of the beam. Here's the weight. This is the normal force from the support at B, and the normal force from the support at C. Here's these given measurements. Now the distance between point B and the weight then is going to be half the distance of the beam. That's 2.6 divided by 2. Now the reason half the distance of the beam, or half the length of the beam, is because I'm assuming the beam to be uniform, and so the weight would act, well, the weight always acts through the center of mass, which on a uniform beam is in the middle of the beam. So the distance here is 2.6 divided by 2 minus this piece on the end here, minus 0.7. And the distance between the support at B and the support at C is the length of the beam minus 0.7 and minus 0.4. That's these extra ends here. All right. Here's the free body diagram. Now, if I want to find NC, this is what I'm wanting to predict because that's what I measured here. So I'm wanting to predict that number. So now I'm going to do that by taking a sum of the moments about point B. So here's the sum of the moments about point B. You have the moment produced by the weight. Well, the weight is 4 times 9.81, and the perpendicular distance from the weight to the support at B is this 2.6 minus 0.7, or 2.6 divided by 2 minus 0.7. Then the only other thing that produces a moment about B is the normal force at C. So there's the normal force at C, which is what I'm looking for, times the perpendicular distance. So this equation is easy enough to solve for the normal force at C. Solve for it, and there you go. I get 15.7 newtons. Now that's pretty close to what I got here experimentally, 15.4, but it's a little different. So the question is that close enough? Is that not close enough? We can't just say, it seems close, that's only 0.3 off. No, we need to be better than that as engineers and actually quantify the error, see where that error comes from. Okay, so here's what I just predicted theoretically, and here's the measurement experimentally. Okay, so now I notice I haven't even got to SAGE yet. I'm just making sure I can do it by hand. So I've done it by hand. Now let's move on to the SAGE part. And let's just try to predict, basically do this calculation right here in SAGE to try to predict this 15.7 newtons. Okay, now some things that I used to make this calculation. I of course needed the mass of the beam, I needed gravity, the length of the beam, and these lengths 0.7 and 0.4. That's the length from A to B and from C to D here. So here's my free body diagram with points labeled. Okay, now let's go to SAGE. So if you forgot where to go, let's go to Google, type in SAGE Math, go to that first link. We're using SAGE Math Online, so you don't have to install any software on your computer. You can just do it all directly on the cloud. Now I've already made some folders here. These are projects. So I've got a project named Engineering Mechanics. I'll click on that, and I've already got some files here, but we're just going to start a new file. So I'll just click on New, start from blank. Let's call this SAGE Project Demonstration. And I want to make a SAGE worksheet. So click on SAGE Worksheet, and it's going to bring up a blank SAGE document. Now I'm not going to take this video to explain everything about SAGE, and exactly everything I'm doing, that should have been refreshed, or that should have been covered in engineering skills. So if you're totally lost, go refresh from engineering, from your notes and engineering skills. Okay, so the first thing I want to do is just basically define some variables that I need to make this calculation, such as the mass of the beam, the length of the beam, length from A to B, and C to D. Okay. Now, a good SAGE document or any good program should be very well documented. So make sure to have a lot of comments. So a number sign denotes a comment. So here I'll define measured values needed for a calculation. Okay. One of those, let's define the mass of the beam in kilograms. Okay. Now let's do it. So I'm just going to call it beam mass. And let's define that beam mass to be 4. Okay. Now I'm going to hold shift and press enter to make sure that it actually works. And it's sitting there calculating. Come on, there you go. Now it finally finished. Holding shift and pressing enter is the same thing as making sure your cursor is in this cell and clicking on the run button there. Okay, now I started out very small and clicked on run because I want to make sure that everything in here is working, make sure there's no errors. For example, let's say you actually had a space in between, you had 2 words, beam space mass. This is wrong, so if I ran this, oh, it gives me an error. What does it say? Invalid syntax. That means, hey, I'm using a name or there's a space somewhere that I shouldn't have. Okay, so let's take that out. Press enter, or shift enter, sorry. So now I know everything in this cell works. Okay, so now let's go through and add to this cell now that I know this works. What other measurement do I need? Well, I need the length of the beam, and that is in meters. Notice in the comment I'm telling you what units this variable is. So let's just call this, whoops, sorry about that. Let's call this variable beam length, and that was 2.6. Now go ahead and press shift enter to make sure that works. Okay, it did, no error. That's good. Let's move on. Let's do the length of AB. So I'll just call this length AB. Notice my variable names, they may get long, but at least you can read them and know what they are. And the comments tell you what they are. What was that length from A to B? It's 0.7. The length from C to D is 0.4. So let's put that in. Length AB is 0.7. And the length of CD, let's call that length CD. Let's make that 0.4. Press shift enter. Okay, hey, everything works there. That's nice. Okay, so no errors so far. Now I'm going to start a new cell. You could actually continue to add to this cell, but let's just use this cell for defining the given information. And now let's actually try to go make a calculation. So now I'm going to calculate the predicted normal force at C. Okay, what is that equation here? So basically I want to type this equation into SAGE. Alright, let's do that. So I've got, instead of typing in 4, I want to take the beam mass. So let's just type in beam mass times 9.81. Let's come back here, times the length of the beam divided by 2. Okay. Times beam length divided by 2 minus this 0.7, and that 0.7 is actually the length of AB. I'm just going to copy paste, which is actually pretty good. You need to, I would get in the habit of using copy paste rather than typing everything out, because if you make one mistake and actually misspell something, you're going to come out with an error. Okay, so I need all that divided by, what do I want to divide it by? Let's go back to this equation. 2.7 minus the length on either ends. So that, I'm sorry, 2.6 I meant. This is the beam length minus the length AB, and then minus the length CD. Okay, now let's run that. And there it is, 15.696. So that's correct, 15.7 newtons. Okay, hey, so I've made a calculation. Let's actually give this a variable name and let's call it the predicted answer. Okay, but notice the number is gone. That's just because this line won't display it, because all this line does is assign this number, which is the 15.7, to be stored in the name predicted answer. So if I want to show it, I could just type this name again. Actually, let's just copy paste it. Oops, sorry, not there. Let's copy paste it down here. And there's the 15.7. Okay, so we're doing good. Now you say, okay, well this is nice, but where's the little slider bars which can make everything change, which can make this answer change? Well, what I want to do now is I want to calculate this answer again, but make it in a way to where I can change this number for the mass of the beam to be, what, 4 plus or minus 0.1, and see how that affects this predicted answer. Okay, so to do that, let's go in and let's actually define. Let's define these uncertainties that I had with each of the measurement. So the mass of the beam is what, 4 kilograms plus or minus 0.1. So let's type in that uncertainty up here. So let's do this. Put another comment. The uncertainty of the beam mass, or the mass of the beam. So let's just call this uncertainty beam mass, and let's make that 0.1. I'm going to press Shift Enter to make sure that worked without any mistakes, and it did. Now let's come down here and let's add the uncertainty of the length measurements. Okay, so let's call this, spell it right, uncertainty of lengths. And that uncertainty was 0.005. Okay. All right. Okay, so that works now. Now I'm going to get into actually making the slider bars. Okay, I'm going to start out with a very simple example, and then we'll just build up from there. Okay, so the way you do it, so notice I'm starting at a new cell down here, not adding on to my previous one. So here, let's just say making the slider bar function here. Okay, let's start out. You type in at and type in the word interact. And then you need DEF for define, and then I'm going to name a function. Let's just call it, I don't know, my slider function. You can make this name up, but at interact needs to be there, and define in a space. Okay, then I need to open up the parentheses. Then let's hit enter, and you actually need to press a tab. Okay, the tab's important. Now let's just try to do one very simple thing. So let's see what this does. Let's do 6,8. Okay, put a colon there. A colon there. And let's come down here and let's type down print A. Okay, so start out with this and press Shift Enter, and let's see what this did here. Okay. So this is an extremely simple example, but now this variable A can be changed on a slider bar between the values 6 and 8. And then this just says print A. So that print A makes that output right there, that's 6. And here's the slider bar, and notice on the very left, the minimum value, it's a value of 6. So this value right here shows what the value of A is. And notice I can slide it and change it. Now it's 6.88, and 6.88 is, or 808 is printed there. I can slide it all the way to the right, and it's a value of 8 now. Okay, so now let's actually add a little more. Okay, if I put another comma, the next thing it will be is the intervals. So let's just try that. Here, let's make it 0.1, see what that does. Okay, now notice when I slide A, this value only increases by increments of 0.1. So there's 6.6, there's 6.7. Okay, this is the increment that the slider bar would change. We can make that small. Let's make it 0.001. Okay, and the next value, if I put another comma, then let's say put 7, what that does is that starts the slider bar in a certain position. So instead of starting it on the far left, this starts it in the middle at 7. And then I can drag it wherever I want to from there. Okay, can run that. So again, the minimum value, maximum value, the increment, well, let's just make it small, and then the default or the starting position, let's say. That's essentially the starting position. Okay, now instead of printing just A, well, I could do something to A. I can make a calculation of it. Let's say make 2 times A. Okay, so now instead of printing just A, it prints 2 times that. Right now the value of A is 7, so it prints 14. I could drag it down here. Okay, that changed this, and now this is 2 times that. Again, so you can make whatever calculation you want. Let's make it -2. So that's 2 times 7, which is 14, minus 2 is 12. You get the idea. Okay. And here, let's just add a little more complexity. And let's make this calculation stored in a variable name. Let's just call that answer. Okay. And now I'm just going to print what's called the answer. Okay, so now I just store this in a variable name and print answer. Now notice I'm making very small changes and running it, and the reason I do that is because I want to make sure everything works before I type in lots of information, or else it's hard to find where the error is. Okay. So let's say now, instead of just made up numbers here, let's say I want this thing to be the mass of the beam. That's going to be one input that I put in. Okay, so the mass of the beam. What's the default, or what's my mass of the beam? It was this number 4 up here. That's defined in beam mass. So let's do that. So I'm going to replace the 7 with beam mass. Now I want the slider bar to go, here's beam mass minus the uncertainty. Okay, the uncertainty of the beam mass is 0.1. So the beam mass can vary between 3.9 and 4.1. So if I take beam mass minus the uncertainty, that's the lower bound. And what's the upper bound? Well, the upper bound is going to be beam mass plus the uncertainty. Okay. And now let's run that to see. Okay, that's nice. 3.999999, that's pretty much 4. And we can slide this and it works. Okay, so we're getting somewhere. I've added in one slider bar. Okay. Here, so let's call this end of the beam there for beam mass. All right. Oh, I got an error. What happened? Okay. Now these error messages are actually really helpful. And look down on the bottom line. The bottom line says the global name A is not defined. So see, I changed this variable name from A. I called it mBeam to represent the mass of the beam. And look here though, I'm still using an A. But is A defined anymore? No, it's not. Okay? So yeah, that's where my mistake is. So I could replace this here. Okay, make sure to get rid of A. There we go. Okay, now I could put comments in here. I actually probably should. And this says define slider bar for mass of the beam. Okay, based on the uncertainty. I need to learn how to type. There we go. All right. Make sure it works. Okay, everything works fine at this point. Now what I'm going to do is go through and try to put in a second slider bar, because I don't just have mass of the beam, I've got some other variables as well. I have a variable like the length of the beam. So let's go try to put in another slider bar. So I'm going to do it here. This is in between those two parentheses. Let's put comma, press enter. Now I need to tab over so it's on the same tab level. And let's just call this L beam for length of the beam. Okay. Now, instead of typing in again, you will make less mistakes if you copy paste stuff. So I'm going to copy paste what I have for the slider up here in the mass of the beam. Okay. Now, before I change anything else, all I'm going to do is just run it. Okay, to make sure I don't get any errors. And I don't have another error. That's nice. So now look here, I've actually got two sliders now. Okay, one for mass of the beam, one for length of the beam. Okay. Now I just need to go through and change what's inside the slider bar here to actually fit what I'm trying to define. I'm defining the length of the beam. So instead of beam mass here, let's come up and get this variable name called beam length. Okay, so everywhere there's a beam mass, let's replace it with beam length. There and there. Okay, and then let's use the uncertainty for the links rather the uncertainty of the mass. So let's replace it with that. Replace it with that. Okay. Okay, now we're working. Yep, it's working good. No error. Okay, now one thing I'm going to do is instead of, so notice here, this slider bar is just named mBeam. What if I want to type in a nicer statement rather than just having it be this name? Well, you can actually do that by adding in another, we call it argument, adding in another spot inside this parenthesis of the slider function here. So go to the very end in front of the parentheses, and I just want to add a new label. Instead of it being mBeam, I want to add a nice label. So let's just put a comma right there, and let's type in mass of the beam, and let's make it kilograms. Notice I had to put in these a little colon there in that parentheses, single parentheses. Okay, well, let's run that and see what that does. Okay, no error. All that did is put in this nice label here called mass of the beam. Okay, now let's do the same thing. I know that works there, so let's put it in the beam length, and let's call this length of the beam. Change the units to meters. There you go. So now these are nice pretty labels here. Okay, so now I'm going to go do the same thing. Now instead of for length of the beam, let's do it for that length AB. So I'll add another slider bar by putting comma here, entering. Okay, I just copy pasted this line, but now let's make this be LAB. And let's go use these links here, LAB. Instead of beam length, let's replace it with LAB. And this is the length AB. Run that. Okay, now I have 3 slider bars. That's good. And no error. Okay. Now let's take this one, copy paste it, put a comma again, same process, but notice I just do one thing at a time so that if I make an error, I know where the next, I know where the error is. It's in that line that I just added. This would be length CD. And so let's go get the length CD up here. Copy that variable name. And let's put it there. Put it there. Put it there. And let's rename this to be CD. Great. Okay. Now these are the definitions of all the variables that I need to make my calculation. Mass of the beam, length of the beam, and these other 2 links here. Now I just want to make the calculation. Okay, after the end of this colon here, I'm just going to put another enter. You can put a couple of them just to make it look nicer. I'm going to run just to make sure everything's still working with those extra lines I added. Yeah, those extra lines didn't make a difference. It just makes it look nicer. Okay, so here's the definition of my slider bars right there. Now, what's the what I want to calculate here? I want to do the same thing that I did up here, but now instead of using these variables called beam mass, I want to use these variables that are defined by the slider here. Okay? Because notice, like this beam length, that beam length is just a number. Alright, I can evaluate it. It's 2.6. Alright, if I change this right here, is this number up here, oops, sorry. Did that number change? No, it didn't. This 2.6 is stored in this name beam length. Okay, I've got a new name called L beam, which is what this slider bar controls. That controls that variable called L beam. Okay, so let's make the same calculation here. Let's do the same thing. So I'm going to copy paste this line in here. I want to make sure it's tabbed over. Now I'm not going to call it the same thing. I'm going to call it the variable predicted answer. Let's give a comment on what this is. This is the predicted answer for the normal force at C that will change with the slider bar values. Okay, so now instead of using beam mass, let's use N beam. So let's replace it there. And now instead of using length beam, or beam length, sorry, I'll use this L beam here, because that's what the slider bar value is. Here's LAB, so let's replace that. Replace it there. And use the slider bar value for CD right here. And now I want to display that answer. See what happens. Okay, here we go. This is awesome. I've got 15.7. Now watch this number change based on the value of these slider bars, because now this variable predicted answer is based on these slider bar values. Okay, so if I change the mass of the beam from 4 to 4.1, well, that changes the answer to 16.08 newtons. What if I change the mass of the beam to 3.9? That's still within my uncertainty range. Well, that changed the value to 15.3. So this slider bar shows how much changing the mass of the beam within its uncertainty will actually change your answer. What about the length of the beam? If I change that one, does that change the answer much? No, not really. From 15.71 to 15.69. That doesn't really affect it near as much as what the mass of the beam did. Right? There you go. And I can change these as well. So, yeah. Now I've got an answer based on a slider bar. And I'm pretty much done, really. Now the only thing I need to do is I just want to go through and display this in a nicer form rather than just watching a number. It would be better to see a graph. And so I'd like to see a graph where I can see like a little point on a graph move when I slide that. So that's all I'm going to do now, is just basically go through and add the graphing part. Okay, so let's add the graphing part. I've got this cell working here, so I'm just going to come down and I'm going to, instead of adding to that cell, let's just add down here on the end. Later we can go back and add to it once we get these graphs working. So I'm going to make a 1D number line plot just like you see down here. Where'd it go? There you go. I want to make this graph here. So this graph is made up of a couple different things. Basically, I have this blue line, and then this green range here is the experimental range. What I mean by experimental range, 15.4 plus or minus 0.2. Because that's what I measured in the experiment, and here's the range within which, the accuracy, let's say, with which I know that measurement is accurate to. Okay, let's first start out and let's just see if we can plot a line here. So let's just plot a blue line. So I'm going to go to plot, type in plot. Let's make that line just a constant number, so it's horizontal. Let's make it 0.1. You can make it whatever you would like. I'm going to make it 0.1. And let's say the variable is x. Let's make it from 0 to 1. So I'm starting out very simple. Let's see what that does. Okay, it made a plot. Here we go. So this plot is just a line. It's the function 0.1. If I put a multiplied times x in there, well, now it has a slope to it. Okay, then I just want a straight horizontal line, and notice it made the plot from what, 0 to 1. Okay, so I actually want to make my plot from before. What was my predicted answer? My predicted answer was about 15.7. So let's take that predicted answer, let's copy that. I want to make this number line go from the predicted answer minus that uncertainty. Have I typed that in yet? I haven't actually typed in the uncertainty of that predicted answer. Okay, I haven't typed in that yet. So let's actually go and put that value in up here. Alright, what I haven't done is I haven't ever typed in this 15.4, that's the measured value, or this 0.2, the uncertainty for that. Okay, So let's do, this would be the measured normal force from scale, normal force of C. Okay, now what I want to call this here, measured in C for measured normal force, and that's 15.4. And now I'm going to put in the uncertainty of the measured normal force. Run that, okay, and I ran it successfully with no error. Okay. So now I'm just going to make that number line go from around that 15.4, 15.7, it doesn't matter. Basically, I'm wanting it to extend, you know, a little bit to the left and a little bit to the right of the range that I'm working in. Okay. So the range that I'm working in, here, we'll just make something up here. Predicted answer minus, I don't know, 0.3. Whoops. And then let's do the predicted answer plus 0.3. There you go. So now that is a number line that goes from around 15.4 up to 16. Okay? And we can adjust this based on these if we need to. And we can make it all the way down to -5 or +5. Okay? That's nice. Now let's call this a, I don't know, my line plot. Okay? So now I've got a variable name for it. And let's still display it here. My line plot. Whoop. And I got some problem. Oh, I accidentally put in some type of a question mark there. Alright, there we go. That's better. There's a number line. Now let's see. So notice I'm making one plot alone, and then I'll go through and I'll combine them later. So that's how I can make the blue line. Now I want to make this green line right there. Let's try that. Well, that green line, that's the, let's say make plot showing the experimental measured range here. Okay. This type of plot, instead of just typing the word plot, since it's not just a function, it goes between two things, is I'm going to make it a list plot here. Okay, and the list plot is basically I want to put the 2 points that it goes between. Okay, so I'll put 1 point, comma, then the other point. Actually, I think all of those might be. I don't exactly remember how that one works. Maybe I'll put the numbers in right there. Now we'll try that. Let's see if that works. Okay, so the experimental range, what's the far left end? Well, the far left end of the experimental range is going to be 15.4 minus 0.2. So that's going to be this. Okay. This is the x value minus what 0 point minus the uncertainty of that. Okay. Okay, the y coordinate, I want it to be on this blue line. What's the y coordinate of that blue line? Remember, it's 0.1. That's what I defined here. There's that 0.1. Okay. Now let's copy that. And here, let's make it plus. Now let's see what this works. Oh, that's nice. Actually, what do I have here? I just got one small little point there. Okay, you actually see this point and this point. Here's the point at 15.2 and here's the point at 15.6. Now basically I just need to add some nice pretty graph stuff that would basically connect those two points with a thick green line. That's all I want to do. I just want to say, hey, connect those 2 points with the big thick green line. So let's just type in the code to do that. So here's the last parentheses for my list plot function. I'll put a comma inside that last parentheses, and then this is an option called plot joined, and let's type in the word true. That says I'm going to join the 2 points. Now I want to make the color equal to green. Okay, let's see what that did right there. Notice I'm just going to run it before I keep adding too much. Okay, that's nice. So I've joined them, and now it's green. Okay, but now let's make it thicker. So let's put the thickness equal to 8, and let's see what that does. Okay, now it just makes that line thicker. And now I could actually add a legend to it. So let's type in legend underscore label. And now let's put a name. Let's call this the experimental range. Let's see what that does. There it goes. So now that just put in this nice, pretty looking label up here. Okay, so that plot works. So let's call this the experiment range plot. Does that work? That works. All right. That's nice. Here's the experimental range plot. Now let's see how would I actually put these together. Let's see if I can do that. Let's make a variable name called all plots, and let's put both of them together. So that says I want to put in the my line plot. And add it to this plot here. All that, it didn't show it, all that did is assign it. Now let's tell it to give me all plots. There you go. Alright, notice this number line, it extends far to the right, but not far enough to the left. So I can change that by changing this. Let's make it go minus 0.8. Let's see what that does. Okay, so that just redefined my line plot. Now let's run this one again. There you go. Now it extends to the left a good amount. That's nice. Okay, so what if I want to put a label on this and say, what in the world does this x-axis mean? What do these numbers mean? I need a label axis. So the way that I can add that label axis is just putting a dot here and typing axis underscore labels, just like this. Now the first label's for the x-axis, and those numbers are force in newtons, and the second one's for the y-axis, but the y-axis really doesn't mean anything here, so I'm just going to leave it blank like that. Okay, I'm not going to type anything in. See what that does. Okay, it evaluated, but nothing showed up. That means I haven't told it. Let's just show it. There you go. So now I've added this label there. Okay. Okay, we're doing good. Basically, the only other thing I need on this plot now is I need that variable I need the variable predicted answer. Okay, here's the experimental range, but I want to see if my predicted answer falls within this experimental range. Okay, so now let's go back, and now that I know all these plots work, let's go put these plots into this function up here. Okay, into my interact function. So I'm just going to do some copy pasting here. Let's copy paste my line plot. I know that works. So now that I know that works, let's just say define the plots here. Okay, there's my line plot. Now let's come get the experimental range plot. Oops, so let's copy that. Let's put that in. Notice it carried over to the second line. That's okay. No problem. And now all I did was add those plots together like this. So let's copy these. Put it up here. Oh, okay, if I run this, it's probably going to give me, actually it didn't give me an error. I would want these to be over on a tab though. There we go, let's try this. Alright, it's not showing the plot. Notice here it's still only showing this 15.6. That's the printed variable answer. I can change that just by using a function called show. So I type in show, open parentheses, make sure I close my parentheses. So now this will just make sure to show all the plots here. There you go. Notice it actually got rid of my printed variable answer. I don't see that 15.7 anywhere, but I want to see it. So let's just maybe try to change the order here. Let's change that. Let's put it up at the top again. Oop, that's on the wrong tab. Let's get it over. Let's see what that did. So I'm first going to print the variable answer, then show all plots. Does that work? Yeah, that works. Okay, there's the variable answer, and here is the plot. Okay, now the last thing I'm going to do in this video is just show you how to actually add the point of this 15.69 that will move. And that's the variable answer. So let's go add another plot, which is a plot of the point of that variable answer. So let's define plot of the point. All right. To define that plot, so let's call this the variable answer plot. It's just a point is all, oops, sorry, it's just a point is all it is. So there's a function in Sage called point, okay? And then all I'm going to do is put in the coordinates of that point. The x value of that point, all it is the variable predicted answer. And what's the y value of that point? 0.1. That's what I defined for the number line. Okay. So now I can take this plot and I'm just going to add it to the others. Okay. So now all plots, you've got the line, experimental range, and the number. So let's run that and see what that looks like. Okay, look at that little blue dot that showed up there. See that? That's the point. That's at 15.7. That's good, but that's hard to see. So let's just make it bigger. So let's add some other options here to the plot, or to the point function, and just make it a little bigger. So I can change the size. Let's make the size equal to 300, see what that does. Okay, it's got it nice and big. And you can do some other things. I can make the color different if you wanted to. You could make it red. That's just going to change it red. And I can actually change the marker to be a diamond. There it is. Now it's a big red diamond. And last, I want to make a ledge. I want to put it in the legend. So I got the experimental range. But now I need to add a legend to this. So remember how I did that? I typed in legends underscore label. And let's type in a label for this. And this is going to be the prediction based on slider bars. Okay, now we're pretty much done. Watch this. Now if I change the mass of the beam to be bigger, watch what happens to that red dot. Oh, it moves further, the red diamond, it moved further to the right. Now what I want is I want this red diamond to be within the green range. That means that my predicted answer falls within my measured experimental range, which is 15.4 plus or minus 0.2. Right now it doesn't. Okay, but let's change some of these uncertainty. Let's move this one all the way to the left, and now it does. You see that? So what this means is that my prediction actually matches my experiment, because when I use the predicted, or when I use the measured values within their uncertainty range, that the predicted answer finally falls within the experimental range. Like you see here, that red diamond is now within the green experimental range. Watch this. If I move the length, let's say CD, did that change the answer very much? No, it didn't change the answer very much. Notice that red diamond's not moving very much. Okay, so this means that if you were to say that, oh, the reason, I have that error is because I didn't measure the length CD right. Well, that doesn't explain a lot of error. That just explains this little bit of actually what, maybe 0.005? How many newtons does it change it by? From what, 15.7 newtons, now it's 15.63. So I only changed it by just a very little amount, right? But maybe the uncertainty of the mass of the beam, that would explain a lot more uncertainty. So this gives you a good feel at which measurements actually affect the answer more. So which ones are important, or which ones are important to get more accurate, and which ones aren't. Okay, that's nice. All right. I think sorry. Let's do one more thing, and that is based on this here. I want you to calculate the percent error of your experimental result based on the theoretical prediction here. I also want you to, where'd it go here? Yeah. This point, I want you to rank the measured inputs according to the significance that each one affects the answer, one being the most significant. So for that, does the length of the beam change the answer the most? No, that one doesn't. It's the mass of the beam is what changes the answer the most, so this would be the most significant one. Okay? I'm going to add in one other calculation here. If you look right here, there's this top line that says percent difference of the calculated answer based on the slider bar value. So what this means is that if I change a slider bar value, what percent does that actually change the answer by? So I want to make that calculation. So let's do that. Okay. To do that, it's just basically a percent error calculation. I'm just going to put it down here. We're just going to print. Now the percent error is something divided by something else times, times 100 to make it a percentage. Okay. So let's put a comment on what I'm doing here. I'm calculating the percent that the answer, that the variable answer, let's say calculating the percent difference of the variable answer based on the predicted answer. Alright, so based on the predicted answer, what was my first predicted answer? It's up here. It's 15.7. So let's get that 15.7. That's what's going to go here. Now what's going to go in the numerator? Well, the difference between the variable answer and the predicted answer. So there's the predicted answer. Where's the variable answer? It's right there. Okay. Let's look at this. Alright. So it's a really small number right now, that negative 2.71 times 10 to the negative 13th. This is a percentage. I wanted to add a percent sign. So on the end of this print, I'm just going to put comma. Let's put a percent sign like that. Alright, that's better. I think you could even, let's put one in front here too. Alright. I can even put equals if I wanted to. There we go. Percent difference. Let's call this a percent change from the slider. Okay, so here's what this means. So right now it's pretty much 0%. That's because all the slider bars are at their default values. It's their optimum values, right? It's like I measured 4 kilograms, so the mass of the beam is at 4 kilograms. I measured the length of the beam to be 2.6 meters. I've got the slider bar at 2.6 meters, so of course the answers match up. But watch this. If I change the mass of the beam to be 3.9 rather than 4 kilograms, how much did that change the answer by? It changed it by negative 2.5%. So it reduced the answer by 2.5%. What if I move it all the way to the right? So now the mass of the beam is 4.1 kilograms. Okay, now that changed the answer by 2.5%. So totally, the uncertainty of the mass of the beam results in a 5% change in the answer, right? From negative 2.5 right there to positive 2.5. So the uncertainty in the mass of the beam changes the answer, or can change the answer by up to 5%. Now let's look at what about the length of the beam. If I move it all the way to the left, that's negative 0.08%. Move it all the way to the right, it's 0.08%. So 0.08 times 2, right? 0.16. That's 0.16%. So the uncertainty in the length of the beam only changes the answer by 0.16%. That's not very much. So that's what this shows you here. It shows you how much these slider bars, the uncertainty in these values, which is measured by the slider bars, how much the uncertainty in those values changes the answer. Alright, so that's a long video. Sorry it's not short, but at least it walks you through step by step of how to build up from the very beginning. So you should add your own personal comments. You may have more variables than just, more inputs. How many inputs did I have? I had 4 inputs here. You may have 6 inputs. You may have 8. I don't know. It depends on your project. So, but this just kind of shows you how to build up from the very beginning, adding one thing at a time so that you don't create a large cell and then you run it and you have a mistake and you get an error, you don't know where the error is. If you add one thing and then run the cell, add another thing and run the cell, you'll keep from making mistakes, or it'll be easier to find your mistakes. Okay? There you go. Hope you enjoy. If you have questions, come talk to me, but this should be pretty good. So catch you later, guys.